Um, well, I'm not sure if people are watching me. I am being recorded on what I think is a practice session, but until I hear differently, I will keep going. And what I will do now is share my screen. And it is not letting me, it says I'm sharing my screen. So I will go ahead and start. And until I hear differently, I will keep going with this. Although if you, let me just send something in the chat. Check the lobby. Okay, supposedly we are in progress. I am not getting much support uh, from the PTC staff. So if anybody is able to assist me with this, that would be great. I see Kaylin has joined. Maybe Kaylin, you can.
Good day. Yes, it is currently being recorded, and I believe that you are meant to record.
So should I keep going with the practice session? Kaylin, should I keep going with the practice session? That's what I'm on at the moment. I apologize to everybody. I'm not sure what is going on. I'm not getting much information here. So I'm not sure what's going on. I'm not sure if anybody will be seeing this, but I will start anyway. So good afternoon. My name is Brad Bass. I am a status professor at the University of Toronto. It was over COVID. I started to re-engage my interest in philosophy back in 2020. And quite by accident, I discovered a formal formulation of what is called the simulation hypothesis. And this is what I want to introduce to you today. So what I want to do is I want to tell you what it isn't. Because I had a number of different ideas of what I thought it was if before 2020 and what it is, how it's supported by the gaming community, especially massive multiplayer online role-playing games, how it's supported by systems theory and some of my own work, the challenge of free will. Can we be fooled by non-player characters? And can we be in a simulation without NPCs? I think this will be critical to whether or not we can accept this hypothesis. So basically, the question we're asking is our universe a computer simulation? Meaning, are we essentially pieces of information or pieces of code in somebody else's computer? Now, what I'm not talking about is philosophers who've spoken on the issue of living an authentic life as opposed to something that is inauthentic. That's an important philosophical discussion, but that's not what we're talking about here. But I would encourage you to look either at Heidegger or Hannah Arendt to investigate this idea. We're also not talking about the idea of living as a simulacra, in which the representation of something comes to represent the thing which is actually being represented. Uh, Baudrillard is actually a very complex writer. It can be extremely difficult to read him, but well worth investigating this if this is something that already interests you. Um, we're not talking about games in the sense of that life is a game. Uh, we're going far beyond that. So but you'll see where gaming does in fact play a role in the development of this hypothesis. And we're not talking about the matrix, although there's a lot of similarities to the matrix, and there are many authors who essentially draw on the ideas in the matrix to support this. The difference is in the matrix idea, there are real human bodies. They're just not operating in a real world. In the simulation hypothesis, there are no bodies. Everything is code. So, so what is the simulation hypothesis? It was first put forward by Nick Bostrom in 2003, and he put forward an interesting idea. He said, look, we might be living in a simulation. He didn't say we are, he said we might be. And he never even said we would know. He just said we might be able to increase the probability of knowing that. And he made the assumption that we would develop the technology that would allow us to do this. So the technology would be technology that would allow us to create our own simulated universe. Now, if we develop this technology, that doesn't mean we will use it to create a simulated universe. We might end up destroying ourselves, therefore that would supersede any other work that we would do in this area. We might develop the technology that we could use to simulate a universe, but decide not to use it for that purpose and just basically do some interesting things with smart cities and artificial intelligence. Or we might develop the technology, such as has been started with massive multiplayer online role-playing games and things like Sim Earth, and then go on to develop completely simulated universes. What Bostrom said was, if we choose to do this, so doesn't mean we will do it, but if we choose to do this, then there is nothing to say that we ourselves are not living in a simulated universe. So if we can build a very lifelike universe in a computer, then there is no way to prove that we ourselves are not also living as a simulation in somebody else's computer. That's what the hypothesis says. So it doesn't hypothesize we're in the simulation, it hypothesizes here's the two things that have to happen. One, we have to develop the technology. And two, we have to use it to build our own simulated universe. Only then might this hypothesis go from being a hypothesis to being the truth about our universe. Now, there are people who take this very seriously and are looking to prove it right now, but that's not what Bostrom was saying. So phase one, The first option, intelligent civilizations never get to the stage where they can make these simulations because they wipe themselves out. Or they do get to the point, but then choose for some reason not to conduct these simulations. And the third option is we get to the point, we develop the technology, and we build the simulation. If we can build it, we are overwhelmingly likely ourselves to be in such a simulation. So it's kind of an interesting idea. The best way to prove we are living in a simulation is to essentially build a simulated universe on our own computers. Now, this idea is not new. Here's what the really fascinating insight is. This idea is at least over 2,000 years old, maybe. It basically goes back to the dawn of religion and the dawn of philosophy. So Plato talked about shadows in a cave. Essentially, he said, we are like prisoners in a cave, and all we can see are shadows from a light source behind us of what the world might look like. We're not seeing a real world. In Asia, Buddha said, reality is a mirror reflecting our inner world. But it's essentially what Buddha is saying is, look, what you think is reality is coming from inside of you. It's not outside of you. It's not an independent, existing physical thing outside of you. So already, over 2,000 years ago, philosophers were questioning this idea that reality was in fact real, or we had access to it. I'm going to flash forward to Kant. There's some people who say that every single piece of thought in the Western world since Plato is really just a commentary on Plato. All you've been learning in school is a commentary on Plato. Other people said, well, actually, no, what you're learning is a commentary on Kant. So Plato and Kant may be considered the two most important thinkers in Western thought. So Kant had this idea that our minds are hardwired to see what's outside of our minds in a certain way. So the world we see is not necessarily the real world. It's the world our brains allow us to see. Perception is really only interpretation. And Kant was the first one to formalize this, but it's become so important that essentially modern neuroscience has accepted and developed this idea. If you decide to pursue neuroscience, you are essentially working within a Kantian, or not what we would call a neo-Kantian framework. So if you have an interest in neuroscience, whether through artificial intelligence or through biology, you should probably try to understand what Kant was saying. The next one is Wittgenstein, and Wittgenstein's an unusual choice because he didn't really write in this area at all, but Wittgenstein said something very interesting. There were two Wittgensteins. What he wrote, and I'm going to speak out what he wrote in his first incarnation, not the second Wittgenstein. In the first one, he talked about this idea that the logic of our sentences is the logic of the world. So essentially, what we take as the world is reflected in the logical composition of how we speak. He talked about the picture theory of language, and he said, imagine that what you're seeing is a picture, and the structure of this picture is the arrangement of its components. And somehow, in order to make this into a real world, we have to be able to share it, and that's what language helps us do. And he took this idea from a court case. And you may still see this in a court case where people will use physical models to illustrate something that happened. And this is where Wittgenstein said, hey, wait a minute, that inspired him to this idea. And it's in his first book called, the short form of it is the Tractatus or Tractatus. Now you might argue, hey, how can that be? Yes, Wittgenstein was fluent in German and English, maybe French, but there are so many languages on the planet, and they're so different. So, for example, there are so many languages. In French is mais il y a tellement de langues différentes. Not that different from English. Below that I have Hebrew, aval yesh kol kach harbe shafot sonot. Turns out the structure of the Hebrew and the French are pretty identical. And below that is Japanese. My Japanese pronunciation is not so good. But Chomsky always I pulled those three languages because Chomsky always pulled actually English, Hebrew, and Japanese. And he always kept saying, well, if it was written in Hebrew, if it was written in Japanese. Chomsky's point was, although these languages may seem different to us, to an external mind, an alien mind visiting Earth from a different planet or a different galaxy, they would conclude that we only had one language, that essentially all the languages are close enough in grammar to function as one language, which is a fascinating concept. Now, so here you have Wittgenstein saying the logic of the world is the logic of a sentence, and here you have Chomsky saying it doesn't matter what language the sentence is in, the logic is still the same. So why is that important? Because if you're coding something and you want to code people speaking, it's nice to know that you only need really one grammar. Makes your job a lot easier. Now, Zeno's paradox, you may or may not have done this in school yet, but it's very simple. It says, imagine you are trying to catch up to a turtle, and you can only go a maximum of half the distance. So the turtle, let's say, is a kilometer ahead of you, you can go half a kilometer. Now you have half a kilometer left, but you can only go half of that distance. And then so that's a quarter kilometer. And then you can only go half of that quarter, an eighth of a kilometer. Well, what Zeno reasoned is you would never catch the turtle because you could never go the full distance. You would always be only advancing half of the remaining distance. So essentially what Zeno was arguing, our world is not continuous. Our world is discrete, and the only way to resolve this idea is to say, yes, it is discrete, but there is some limit to how discrete it is. There's some small unit that is the basis for all of the other units. So as long as you're not getting down to that unit, the world will appear continuous. So here's Zeno's paradox, and in the corner you see a very, very small square. That represents the fundamental grid size. Now, that's important. If you're building computer simulations of a world, you essentially have to build something that may look continuous, but it's really based on very small pixels. Now, there's a physicist, Zora Davuti, and so she accepts the simulation hypothesis, and she said, look, if you're going to build a universe on a computer, you're going to have to discretize space-time to save on computing resources. So similarly, if our universe is a simulation, it has to be discretized. There has to be some unit, very small, but some unit at which point we'll see a grid. Some people say that's the Planck constant. That defines the unit. But Zora is looking for it. So Zora is trying to show what is necessary for us to basically prove that the universe is discrete, not continuous. And if she can do that, that will help support the simulation hypothesis. Now, even before Zora, we had Ed Friedkin, who's a computer scientist. And again, if you are a computer programmer, you should find out who he was. And Arthur Schopenhauer, a philosopher after Kant. And they both said some very interesting stuff. I'll start with Schopenhauer. Schopenhauer basically said, look, Kant made an error. He made an assumption that although we can't have access to the real world still basically has the type of information we think we're seeing. So here's my hand. I don't know, you can't see my hand. Look at your own hand. If you're Kant, you're not seeing what's really there, but something is there. And so there's still a reality that's composed of the objects you're seeing. You're just not seeing them as they really are. Plato might have said the same thing. Schopenhauer said, no, wait a minute, I accept this idea that our brains are hardwired to see the world in a certain way, but in that case, we have no access to what the world is, and all we can say about the world is it's a blob. And only when we start to look at things does the blob essentially take shape, change from being an amorphous blob to being something very realistic. Now, that's going to become very important in simulating a universe. Friedkin said that he already was saying in the 1970s that the universe is composed of discrete units of information. And these patterns are all made by a program called Friedkin's replicator. And notice how fine a grid you can get, how what I call small the resolution can be, until you might not even know you're looking at a grid and you're starting to see real shapes emerge from the grid. So the one I just brought up doesn't look like a grid anymore. Here's another example, again, how a grid can be emerge into something else, and here's a number of different examples. In 3D, what you would see is within the grid, shapes emerge to represent the objects that we are looking at. This isn't all that different from Schopenhauer's idea. Schopenhauer could probably accept, okay, the world's not a blob, the world's a grid, and our mind allows the different things to emerge. Now, why is this important? One of the massive advancements in video game in our technology that came from video games was this idea of to be able to render 3D and change the perspective on the screen. But what we're able to do is only render that part of the universe we need. We don't have to have the whole universe in our games. We just need the scene we're in, wherever we are. Similarly, if you're going to build a simulation of the universe, you really don't need to simulate the whole universe. You just need to simulate where people are and what they're looking at, but you don't need to, for example, if there are 18 quintillion planets, you don't need to have each planet being simulated at the same time. You only need to simulate another planet when your pieces of code, us, happen to go to that other planet. So basically, most of your universe can remain as the blob. Very easy in terms of information resources to code. And we have this technology that we only need to see it when we look at it from video games. If you think about it, relativity and gravity are essentially based on a grid. So this, in my mind, this was Einstein's, and also now the quantum gravitation physicists, their biggest contribution to this is that it makes sense to think of space-time as a grid. So the idea that the universe is actually not continuous but a very fine grid is not foreign to science, and obviously it's not foreign to coding. The other thing that's really interesting is thinking about how perception works. So think about navigating a city using a map. A map is a two-dimensional image. It's only a small part of what's really there. But somehow, from that map, you can form a model of what the world looks like. So you can go from the map and get yourself from point A to point B in a new city. And that's because you already have a sense of, if I look at a map of a city, and then I go to that city, I have an ability to relate the map, which is a model, to the city um, where I'm standing. So this is an analogy with perception. And in fact, if you're really interested in this, this is studied in geography. If you really want to be coding games instead of playing them, you should really take some courses in cartography and find out what they're saying about how people go from maps to the real world. So when we look at actual perception, it's in some sense fairly different, fairly similar, I mean, in that we don't see the world. This is what neuroscientists are saying. This is how they're neo-Kantian. We don't see the world. We don't see it. We see only very small bits of it. But our brains take those bits and make a guess of what we're seeing. Essentially, when there's enough data, it builds a model. Now, there have been some experiments in this that have just been fascinating. It wasn't an experiment, but you may remember 2015, the dress that some people saw as white and gold, and other people saw as black and blue, same dress, but no nobody, what I should say, we all saw it as either gold and white or black and blue. You saw one or the other. Uh, Another experiment that was done was a bowl of gray strawberries, which everybody saw as red. Again, why? You have a model of strawberries in your head. You only need a little bit of data, and people could not see the color as gray. If they knew what a strawberry was, they saw it as a bowl of red strawberries. So you see, this happened to me. It's kind of interesting. I was walking down the street from my house to a train station in suburban Mississauga, and in the distance, I saw a dog running towards me. It's a bit unusual to see a dog without an owner where I live, but knew it could happen. So I stepped aside. I figured I'll just let the dog run by me. And then my everything shifted because my brain was making the wrong model. It was telling me the wrong thing. I wasn't seeing a dog. I was seeing a deer. And it was quite a shock to realize that's no dog. That's a young deer running towards me. Another way this has happened, you're walking in the park, especially when the grass is not mowed, and you see what you think is a fluttering piece of paper above the grass. Something stuck in the grass. If you're smart, you will note the color of the paper, and if it's black and white, black or white, you will just stay away because most likely it's a skunk. But if you've never seen a skunk, you don't have a model of the skunk in your mind. And your mind takes a few bits of information in the distance that you think is a fluttering piece of paper, and that's what it tells you. That's how a lot of people end up being sprayed by a skunk. They've never seen one, so they don't have that model. They can't, their brain will not make that association from the bit of data it's seeing. So you see something, your mind says, okay, here's what it is. Here's my prediction of what it's going to be. And it's based on everything else you've ever seen in your life. But what you see is a model. You don't see the real world. The other interesting thing that technology that has happened. So what does that mean? By the way, you don't see the word. It means that when you're coding what someone sees, all you have to really go to is a library from a few bits of data. You don't have to show them everything. They just need a few bits of data in order to see what's there. Fractal landscapes are really interesting. Both of these landscapes may look real, but they're not. They're generated with a mathematics called fractals. And I won't go into what fractals are, but the fact that you can create landscapes from this really allows us to create very realistic worlds to live in. And if you're again building code, it means you really only have to create one complex representation of the curves, and then you can base all your coastlines off of that. It just makes it very easy to go from one shape to all the other shapes. Now, if you're interested in this idea of what we learned from games, I would suggest reading Rizwan Burke's book, The Simulation Hypothesis. And he makes a very interesting comment, which basically is, look, 10 things have to happen for us to have the technology to simulate a universe. And guess what? 5 of them have already happened. We're halfway there. Rizwan can't give us a timeline for the rest of it, but he's pretty sure if we're going to develop all 10, we'll have done it by the end of this century. Not a long time, and given the achievements we're making in medical science, I suspect all of you will be alive at the end of the century. So, but these are some of the major ideas that go into building a simulated universe. Discretize space, only render what is being observed, optimize limited resources, and I said we're on step 5 out of 10. The first 3, if you're a coder and you're coding games, you have to know those 3 principles. Now, Elon Musk, he made this statement based on where game technology has come from since Pong 40 years ago. And I said, if you assume any rate of improvement at all, then games will become indistinguishable from reality. And he said, that's the trajectory we're on. Doesn't mean he's right, but of course he's been right about a lot of things, that have to do with technology. Now, he could have been referring to Moore's law, which Moore's law is this idea of technological growth. And basically it says with a lot of technologies, the development may be very slow, but there's a certain point after which the growth becomes exponential. And this is what's happened in information technology. This is why the development of new phones, computers, etc., advancements are so rapid, because we've gone to that exponential part of the growth curve. So there's this idea, looking at a plot of microchip complexity for minimum cost over time. So a representation of the complexity on the y-axis and time on the x-axis. You can see that we probably crossed the threshold around 1971. And then the curve became exponential. Look at the growth of video games. Here's the history of game budgets. It's somewhat linear, but look at the geometric expansion of project complexity and staff in the gaming world. And you see actually, I take it back, the game budgets look, they do look linear. You could probably fit it with a nonlinear curve, but when you look at the expansion of the complexity of the games and the number of staff, it's nonlinear. I mean, look at the staff and the budgets, and they've grown in a nonlinear fashion. So that may be part of the explanation why games have been evolving so fast. Another part of it is the hardware and software, for other reasons, have been evolving very quickly. Now, there is a challenge to this, but first I want to define this idea of emergent computing, because I want to look at one other important concept. So patterns arise from interactions between agents or between agents and their environments, even if the patterns aren't explicitly coded into the program. So not everything that happens has to actually be coded into the universe. You can allow things to emerge just from interactions of different components. So let's take a look at some ideas from systems dynamics. On the left, you see a tree root ball, but this could represent roots, could represent molds, could represent an octopus. And on the right, you see the principles of dynamic networks. Essentially, the principles of the dynamic networks are pretty much the same as what you find underlying roots, molds, and octopi. So here's a simulation that was done, I think, in about 20 years ago. But essentially, the blob things you see in each map is the growth of a slime mold, and the lights, the dots, represent the growth of a rail system in Tokyo. And basically, what they found was you could use a slime mold to more or less simulate the pattern of growth in the rail system. It followed the same dynamics. Now imagine you're building a universe. Isn't it nice to know that the dynamics you use for the molds are the same dynamics you use for rail systems? It makes your life a lot easier. Here is a simulation that my lab did of a slime mold using software we built called COBWEB. And you can see it's pretty mold-like. The green things are food because they actually help direct the simulation. Slime molds will change direction for food and will stop at food to consume it. And again, you can see now the food is off to the left of the double cluster. And you can see again it's growing this way. And eventually it grew to be a network such as this. Here is a portion of the road network in Canada. And I want to draw attention of the triangle linking Toronto and Ottawa and up around Georgian Bay. And look at that same part of the map, that triangle at the bottom in the simulation model. And now we've sort of put them together. We've taken the network from the map and shown how it fits on the slime mold, and it's a pretty good fit. Trying to see. Now, my student who built this, she did an interesting, it wasn't really a formal experiment, but it was interesting in that she did work with 10 people. And she showed 10 people a map of the road network and the slime mold network and asked them to basically say, are they different? 9 of the people could not see a difference. Only one person said they were different. She didn't tell them what they were ahead of time. She said, can you see, are they different or are they the same? And 9 of them said they're the same. So what do we learn from this? A few principles can be reapplied to a range of systems. Intelligence can be decentralized. I'm not going to get into this a whole lot. If you want to talk about it with me, I'd be glad to talk to you about it. But we're very brain-centric, and maybe we're too brain-centric, and we're whatever the opposite is, we're phobic about. We're life without brains. We have a phobia about that. Allowing for the use of one intelligence spread amongst many, that should be amongst many agents. So we can code in a way that allows for one intelligence to basically be used for many agents. And this is an idea we'll come back to, so I want you to remember that. Now, you may be at this point ready to accept, yeah, I can accept simulation hypothesis. I'm a gamer. In fact, if you are a gamer, you really are the new philosophers or the new physicists. If you get a lot of flack from your parents about spending so much time playing games, say, I'm not playing a game, I'm doing philosophy. So, but what's the challenge? And I'm going to say that I think, and this is my original contribution. I think the biggest challenge to this is free will. And I think right now to accept this idea, you may have to basically make a decision on free will. Do we have it or do we not have it? In the neuroscience community, the consensus is we really don't have it. But in philosophy, psychology, the consensus, I'm not sure what the consensus is. I think it's split. So, does everything start with intention? If it does, then we're talking about free will. Can you make choices between options? If you can, we're talking about free will. Now, those are two things that are inherent to free will. You have an intention. Everything starts with an intention to do something, and you can choose between alternatives. So you have a conscious intention, you make choices, you get to an outcome. There's one more thing that's necessary for free will. Interestingly enough, you may think what I'm about to say is the most difficult pillar to prove. Not necessarily. But the third one is mental acts. Essentially, your mind has to, in some sense, operate separately from your body. It's not just synapses firing. Something about your mind is separate from your body. So thoughts are separate acts than from your physiology. The process of thinking is separated from your physiology. Thoughts essentially, I won't say they have their own life, although in some sense they do. But think of memes. Memes exist outside of us. The whole idea of a meme initially was the idea of a replicating idea like a gene. Instead of a gene, they called it a meme because it was a thought. Well, that separate existence. Very famous experiment, thought experiment. Imagine a person, in this case her name is Mary, she's brilliant, only raised in a black and white universe. Mary's told that something called color exists. She's never seen it, but she's told it exists. She decides to read everything she can about color, and she really understands red. She feels she really understands what it means to be red, the color red. Showing Mary that color is enough to really freak her out. She's never seen red. She may think she knows everything about it, but actually seeing it is an experience that what will happen we can't predict from where she is now, and she can't predict. And this experiment was actually used to demonstrate that thought has a separate existence from body. Now, this idea in its pure form is called dualism and goes back to the 1600s or the 1700s. Descartes is credited with formalizing this. If you talk to most people in the field of neuroscience and other sciences, they will dismiss dualism. And there are other forms of idealism is another form of this. And idealism, the idea is that ideas, what we think, are the primary things that exist. Matter is secondary. So now, why is this important? To have free will, there must be some separation between what you think, mental acts, and the body. So we need intention, we need choices, and we need mental acts that are separate in some way from the body. Turns out, I think the hardest one to show is intention. But most people think it's the third one, mental acts. I think you're wrong. I think the hardest thing to prove is intention. But if you're not ready to accept free will, are you then ready to be an NPC? Because we're obviously not playing this game. Maybe some of you are. Maybe one of you is playing this game. So that means essentially we're the NPCs of the game. Now, free will, right? Intention, choice, causation from mental states. Okay, you need all of those to not be the NPC. So intent, causation. Now, one thing we know that we can attribute to simple AI agents, like simple pieces of AI, something called anticipation. The idea of basically anticipating, predicting what the next step will be. We can anticipate the future, whether it's the next minute or the next year. I wrote a paper in 2000, about 2000, basically demonstrating that genetic algorithms, which are an early form of AI, can manifest anticipation. So intent, I'll say maybe. Anticipation, yes. Choice amongst alternatives, I would argue that in any AI simulation you can do that. Causation from mental states, well, there's a Turing test. I don't know if you know what that is, but essentially, if an AI can convince you it's alive, it's passed the Turing test. Self-referential, well, so far AIs are not self-referential. Well, do mental states exist? Well, anticipation does, and anticipation leads to action. So, if we accept, okay, anticipation is a form of intent, AIs can actually be programmed to choose amongst alternatives, the anticipation can cause action, maybe they could pass the Turing test, maybe I can make you believe an NPC has free will. So you could be an NPC without realizing it. There's another thought experiment about a world where everyone is a zombie, but to each other they don't know that. They're all passing the Turing test to each other. And it goes on to show that this zombie world would not really be any different from our world, meaning that we then cannot prove that we are not zombies. Now here are some games considered that have the most intelligent NPCs that can trick you into thinking they're real humans, and some of you may have played these games. And this is a little bit already, the list is already a little bit old, so there may be other games that allow you to do this. Does that mean we have to accept being NPCs to accept the simulation hypothesis? Actually, we can find support for the simulation hypothesis, again in philosophy, that might allow us to get out of this conundrum. And that's something called open individualism. And open individualism basically says mind is independent of body, but there's only one mind. We all have it. No, not that we all have a piece of it. We all have the complete mind, but there's only one. And every time a person is born, person gets, that whole mind manifests in the person. Now again, imagine you're coding an AI for 7 billion people. You only need one mind. Doesn't that make your job easier? Certainly does. Open individualism is not connected with the simulation hypothesis. I think open individualism supports the simulation hypothesis. And I think the simulation hypothesis makes open individualism more possible. The neat thing about open individualism is it is a philosophy, a school of thought, of consciousness, but it's not old. It's very new, 2004. In fact, you might argue, if you're really into the history of ideas, that it's a bit older, but it doesn't matter. We'll just say 2004. Officially, it's accredited to a philosopher, psychologist, physicist named Daniel Kolak. But again, there are other people who claim that they were working in the same area before Kolak published his work. Now, I find this interesting because I'm the principal behind COBWEB. COBWEB is an agent-based software. It looks like this. These triangles are our agents. When we start a COBWEB simulation, for many years, our first iterations only had one mind given to all the agents. Now you can play around with that. You don't have to use the one mind. You can have multiple types of agents, not just 4, and you can give them all different minds, but it's still the same mind by type. And you can start to see how similar the simulations proceed, whether it's one mind or 4 different minds, or if you have 10 types of agents, 10 different minds. You can start to explore this idea of one mind in a somewhat complex world, in this case 2-dimensional though. So COBWEB is used to explore how systems adapt to environmental change and to explore the role of chaos and complexity. You have agents, which are the triangles. You have resources, which are the foods, the green, the pink squares, and you have black squares, which are barriers to movement. And whereas the food gives the agents energy, the black squares take it away. The agents are genetic algorithms, which means they have all the abilities of genetic algorithms, which I don't have time to go through, so we'll leave that for now. But which means they're basically AIs. They're computers, they're simple AIs, but they can make some of their own decisions, or make you think they're making their own decisions. So, open individualism makes it, if you accept it, it makes it much easier to code your own universe, and software such as COBWEB appears to show it's true, that this is indeed the case, that you can build a complex society with one mind. Now, are we living in a computer simulation? Question you can ask. Are we like COBWEB individual agents but only making limited decisions? Or are we fully conscious and making real decisions? So, at this point, I don't know. I think there's more work to be done. What I'd like to see is more work on these NPCs. Can we imagine, can we write a game where the NPCs keep playing even after we're not there and the game universe evolves? So we get out of the game, but because it's in the cloud, it keeps going, and we come back in and it's evolved to a state we now don't, and perhaps don't even recognize. What if NPCs from ongoing games could share information? Would that change the way they behave? And can NPCs pass the Turing test to fool you into thinking they're actually alive? So I think we have to look at these 3 questions. These are going to be very important to get us on the way to building our own simulated universe. Now, the other thing I would invite you to do is consider joining us in our work with COBWEB, and specifically because you're hopefully interested in this idea, you could explore the idea of what happens in a system with one mind versus multiple minds. When does the system start to make it, become very different? Or can we actually see that difference if we only use one mind? So we meet regularly Wednesdays at 5, except yesterday we didn't meet. I went to the baseball game. So when I go to a baseball game, we don't meet, obviously. Um, uh, and every other week we meet in person at the University of Toronto. Otherwise, we meet online. And then Thursdays, I have virtual office hours. If you're interested in this and opening this door, this is the end of my presentation, but you can contact me at cobweb.ca@gmail.com. And although it's the end of the presentation, it's actually the beginning for you. And I hope you'll join us in trying to open that door. And with that, I will end the presentation. This is being recorded, so I don't know if there's any way in which we facilitate questions. I don't know if anybody's watching at this live, but if there are people there and there are questions, I'd be willing to answer a few questions.
Thank you very much, Dr. Bass, for your time and extraordinary presentation. It would be the time for any questions or about the field in general. Try not to ask the same question twice and instead upvote any question you wish to see answered, if there are any questions. Well, the next event will start soon, so thank you again for your insights. Hopefully, another round of the next event will begin soon in another room in the Zoom. So thank you very much and enjoy the rest of the conference to the participants.
And thank you for sharing your time with me. And please feel free to contact me if you either want to join us or you think of some questions.